Now what we'll do, we'll go to the Nth Order System. We'll start talking about the Nth Order System. And what we'll have here is that we'll start analyzing it, but we'll only look at the first order terms. So let's think about the Nth Order System. What does it look like? So you will have n ports. To have an Nth Order System, you have to have at least n energy storing elements. You may have more, but you have to have at least n. So let's say you have n. And a more accurate way of saying is that you have a system with n energy storing elements. So let's take C1. In general, this could be like L2. We have a CI, CJ, etc., all the way to CN and LN, right? So in general, that's how a system with n energy storing element looks like. So you have an X and a Y output. And the system inside this box doesn't have any dynamics. So now we want to find out what's the transfer function. So in general, we have already discussed this. We know that the transfer function looks like this. There are many different ways to write it. One way is to write it as A0 plus A1S plus A2 squared all the way up. And then divided by 1 plus B1S plus B2 squared all the way up. Okay? So now today what we'll do, we'll determine A1 and B1 exactly. And I'll tell you what the answer is first, and then we'll derive it. And you don't need to remember the derivation, but you need to see it once. So the answer is the following. The answer is that B1 is the sum of all the time, what we call the zero value time constants for all the elements. And what are the zero value time constants? Zero value time constants, so where tau I is 0, for instance, is when you look at this element, let's say element I, and you look at the resistance seen by this element, which we call Ri0, where the 0 is the superscript 0 indicates that all the other elements have been in zero valued. Namely, this guy is an open. This one is a short. This one is open. And so on and so forth. So Ri's, so it's an Ri0 times Ci. Or if it were an inductor, it would be Li over Ri0. So we call these zero value time constants. Now, if we're dealing with only capacitors, sometimes they are called open circuit time constants, or OCTs. But you can see that's not a very good name, because it's a good name only as long as you're dealing with capacitors only. If you're dealing with inductors, then what happens is that it becomes confusing, because the zero value of an inductor is a short. So that's why we call them ZVTs, zero value. So you put zero value there. So that's what B1 is. We claim that's what B1 is. And what A1 is, in general, for an Nth order system, is the sum over all elements of Hi tau I0. Where tau I0 is exactly the same zero value time constants. So once you calculate it for this one, you can use it there. And Hi's are what we call the transfer constant. It's the ith order transfer constant, which is the transfer constant, the gain. It's a low frequency transfer function, called the transfer constant, from the input to the output. So it's H. When Ci is infinity, or Li is infinity, that particular element, because you can see that's what our notation means, right? Anything in the superscript is the superscript of what's being infinite value. It's the index of what's being infinite value. Where Cj, all the other Cj's and Lj's are non-zero, are 0, when I is not equal to J. So namely, all of the other ones, to calculate that, what you do, everything is zero value except for this guy, which is infinite value. So being a capacitor, this is infinite value. Everything else is zero. Zero value. Right? Which you can see, it's kind of a generalization of the first order system. In a way. And that's what A1 is. So now we have to prove this. Okay, and I will do the derivation. It takes like 3 minutes. Because we are going to use the first order result. So here's what we will do. So the way I think about it for the derivation is that, okay, well, let's take the same system with n energy storing elements, x and y, and n ports. And let's just zero value all the elements. Let's take that system and say, well, I'll zero value all the elements. And now in the beginning, let's assume that they're all capacitors. And we'll see how, I tell you how it would be look when you have inductors as well. But let's just do it for capacitors because then I have to write one sum as opposed to 2 sums. But it's exactly the same derivative. So except you keep the Ci, the ith capacitor. And all the other ones are zero value. Right? So what's the order of the system? The transfer function of system, what do you expect it to look like? It's a first order system, right? It has only, this new system, the way I've defined it, has a transfer function, must have a transfer function, called H1 as A0 plus A1s divided by 1 plus B1s. And these are not the same A's and B's as the other one, so you can write B prime and B prime if you really want, but it doesn't matter. It's not the same as the one. Right? So I have a first order system. I know how to determine its transfer function, right? I know what the transfer function of this first order system is. What is it? It's that transfer function. So we know the transfer function of the first order system is what? Of this H1 of S is H naught plus H, well in this, let's call it HI, right? Because this is the ith element. HI tau I 0 S divided by 1 plus tau I 0 S. Why is that? Think about it. What I'm saying is that the transfer function of this system, well, it's a first order system. How do we determine its transfer? What is the time constant of this system? The time constant of this system is the resistance seen by this guy times this capacitance when sources are not. But that resistance is by definition is the zero value resistance. So it's Ri naught because by definition it's the resistance seen by this port when all the other elements are in zero value, right? So I know that tau I 0 is going to be Ri0 Ci. I know that from the first order system derivation. And then I know one more thing. Okay, and what is the Hi? Hi is the transfer function by definition of this system when this guy is infinite value. Which is by definition again, so Hi becomes the transfer function of the original system when Ci is infinity, goes to infinity, and all the other ones are 0. Right? Because we have already set them to 0, the way we define the system. So that's H. And H naught is the transfer function when Ci is 0, which is the transfer function of the system to begin with. Right? So this is a low frequency transfer function. So we know these. But I haven't proven that yet. I've proven that for this system, these are what the parameters are. But I haven't proven that actually the transfer function of the overall system, in that one, A1 and B1 is the sum. So I have to prove that. So how do I prove that? Well, I think if I use another piece of information. Let's say I have only capacitors. How can I get the transfer function for a system with a finite number of elements, blunt elements, is written in a ratio of 2 polynomials in S, right? How do you get S? Where does S come from? The S comes from the capacitors, right? The only thing that can introduce a frequency-dependent element. So an impedance or admittance, the impedance of the capacitor is 1 over Cs. So every time I have a C, I have an S. I have to have an S. So they go plus sigma. So for the first order term, I can only have a linear combination of the capacitors. That's the only thing that gives me a first order term in C, right? So it has to be, let's call this alpha. This is an intermediate variable, right? Alpha 1i, Ci, I from 1 to n times S. Do you agree that the first order term can only have first order, can be only first order in capacitors? Because if you had a C squared here, you had to have a S squared there. So all the S squares come from those. And then the second one is written as Ci Cj S squared I from, you can write it two different ways. So I write it, first I write it the long way, J from I plus 1 to n. So this goes over one combination. So if you go over 1, 2, you don't go over 2, 1. Another way of writing this, which I usually prefer, but it's up to you, is this. It's less mathematically accurate, but more intuitive. So you sum it over all combinations as long as I is smaller than j. And you cover all the combinations. So you go, if you have like 3 elements, you go 1, 2, 1, 3, 2, 3. Now, there's and same thing in the denominator. I can write a similar linear combination with a different set of parameters or coefficients. And then I have higher order terms, right? The third order term would be a three-way sum. It would be sigma ijk, Cijk. Sometimes I even do it this way. So you reduce the rest. Okay? Now, there's one thing here that's a little tricky, and so you may ask the question, say, why don't you have a Ci squared here? Why don't you have a Cj squared? Because the way I've written it, you can't have a C1 squared or C2 squared. You only have like C1, 2, C2, 3s, right? Why is it that you can't have a C1? I claim that you can't have a C1 squared or C2 squared. And I'll answer this question in a minute. Literally in a minute. But let's keep that question in mind. Okay, so if that's the case, then what is the transfer function if Ci is the only element that's non-zero? And all the other Cj's are 0. How does this look like? How would this look like? Is it fair to say that if only one of the capacitors is non-zero, all these higher order terms would be 0? As long as I don't have that Ci squared, right? So let's first, again, make that assumption and keep going forward. And I'll tell you what happens if it isn't. So, and let me tell you right now, let's say if you had a Ci squared here, okay, then that one would not be 0. Correct? So you get a second order system out of a single capacitor. Right? If you had the same index for both of them, if you could have a C2 squared, C1 squared, then if that C1 is non-zero and everything else is 0, then you get a second order system using a single capacitor. Which can't be true. Yes?
I doubt that, because I may say maybe that's because in an nth order system, not a first order system. Well, I mean, when I have multiple capacitors, maybe a second order Ci may appear.
No, but yes, I have multiple capacitors. But this should be valid for any value of capacitors. So that's the argument. I'm saying that if this is correct, this should be independent of the value of the capacitor that I use. So it should be valid for capacitors of 0, and it should be valid for very large capacitors too. So what I've done here is that I've said, okay, let's assume that this is true. This is an n capacitor. But let's say these are all zeros. I can have values of 0.
Yeah, you're right.
And if I set the value to 0, then this cannot be a second order system. It has to reduce to a first order system. So that's why you don't have those square terms. Anyway, so since we don't have square terms, so what happens is that this reduces to what? this reduces in this case, then the transfer function simply becomes A naught plus, so the only term that survives this is alpha 1I Ci S, and in the denominator you have beta 1I Ci S. And now comparing this to that, I can determine what alpha and beta are. Clearly H0 is H naught, which is obvious. When all the capacitors are 0, you should get the zero value transfer function, the DC, the low frequency transfer function, which is fine. Alpha, let's go with beta 1. Beta 1I Ci has to be equal to tau I, which is Ri naught Ci. So therefore beta 1I is Ri0 for this reduced system. When all the capacitors, I set the value of the capacitor to 0 except for 1. And then the same thing from here, you can tell that alpha 1I, then by looking at it, you clearly see it's basically Hi Ri0. So since I haven't made any assumption about this, there's nothing special about index I, this should be valid for any value, any one of the capacitors. Because I just assume that arbitrary index I. So I can plug these into this one and determine their A and B. So this becomes H naught plus sigma Hi tau I0, because remember, this is Hi Ri naught times Ci. The Ci comes from this one. And the Ri naught Ci gives you the tau I times S plus higher order terms divided by 1 plus sigma tau I0 S plus higher order terms, which proves what we wanted to prove. Right? So this is A1, this is B1. So from now on, we use the results. Basically, we know that A1 and B1 are those. Now, these are very, very powerful results, in fact. The one that's most powerful and used the most is this. This is basically called the method of zero value time constants. It's extremely useful, and we'll see several examples of how it can be used. Then this can be the basis of a modified zero value time constant method that takes into account the effect of zeros. And I'll show you how that's done later. But that's the essence of this discussion. Now, one thing that I want you to remember is that this says, so let's continue with this. Now, you remember also there was another representation for this, right? There was another way to write this. There were many different ways to write this. Another way of writing this was, if you factor the numerator and denominator, you wrote it like this, as a product of first order polynomials like that. And if you look at that, B1, we did this calculation before. We saw B1 was simply minus sum of the reciprocal of the time constants, of the pole frequencies. Right? We saw this before. And B2 was the two-way products. It was sigma ij 1 over pi pj when I and j are not equal. And so on and so forth. So, looking at these two, it's very tempting to say, maybe they're individually equal. Because this is an equality, there's no approximation. This sum is B1, and this sum is B1. And it may lead one to think that way. And this is completely, in general, this is not valid. This is not true. This is something that you should remember. That although this sum is equal to that sum, so the sum of the pole time constants are equal to the sum of the zero value frequency, zero value time constants. There's no one-to-one relationship in general. Unless the poles are uncoupled, and I'll tell you what uncoupled is. So in general, this is not true. And there are a lot of cases where people make this approximation. They say, oh, okay, I have a capacitance here, I have a resistance on this node, they calculate the time constant and say, well, okay, so then 1 over that time constant is the pole frequency. That's wrong. I mean, taking a good approximation in certain cases, but it's not mathematically correct. And a lot of times it's not even a good approximation. So you should be aware of this. But this sum is still very useful. And we'll see how it's useful in a second. But let me show you an example where this is for you to believe this, and also see how this is done. Let me show you an example. I'm going to make a very simple example also, but this is a good example because it also shows you how these things are applied. So let's say you start with you have an input voltage source, VI. You have a system like this, and this is VI. So this is let's say this is R. Well, let's say they are the same capacitance, but let's take index them C. This is the first one, this is the second. Same value. What kind of a transfer function, by the way, do you expect from something like this? Low pass, high pass, what do you think? Well, if you want to see what it is, look at it at low frequency and very high frequencies, right? And low frequencies, these are not here, so you get the signals, and the output is the same as the input. The very high frequencies, it's shorter to ground from here. So it's a low pass. Now, how many poles do we expect to see? Well, the answer to that question is how many independent initial conditions can I set on this circuit when I null all the independent sources? So if I null this, I can put 1 volt on this one, and I can put 2 volts on that one. Right? Nothing will happen. It's okay. There wouldn't be any contradiction. So I have 2 independent degrees of freedom, so I have 2 poles. How many zeros do I have? Well, is there any capacitor shorting of which results in a non-zero transfer function? If I short circuit this, the output is 0. If I short circuit this, the output is 0. So there isn't. So there's no pole. There's no zero. There are two poles, no zeros, no pass transfer function. So I can already tell a lot about the circuit before even touch it. So let's calculate the time constant. By the way, do you know what the transfer function of this thing is? I mean, we can exactly calculate it, but I'll do it in a second. So let's do the time constant. So I know that the transfer function should look something like this. Should be 1 plus V1s plus V2s squared, right? That's what we concluded so far. No zeros, 2 poles. That's the most general case. So I know what B1 is now. So B1 is tau 1 0 plus tau 2 0. Let's call this 1 and that one 2. But let's assume they have the same value. So what is tau 1? 0. Tau 1 0 is the time constant, 0 value time constant for this capacitor, meaning that you look at the resistance seen by this capacitor when, of course, all the independent sources are null, but also all the other elements are 0 value. So you null this one, so basically this is ground. And you null this one, which basically means that it's not here. It's gone. What is the time constant? What is the resistance seen by this guy? Tell me. R, right? Because this side is open, you only see an R to ground. So the resistance seen by this guy is simply R. So it's RC. What is tau 2 0? Again, this is ground. So tau 2 0 is when the resistance seen by this guy, when this one is null. It's not there. What is the resistance seen? 2R, right? R and R to ground. So it's 2RC. So this is 3RC. Okay? Now, you can calculate this transfer function directly from KCL, KVL. That's probably the only time I could write KVL, KCL is here. The only reason is that I want to show you something. But I'm not even going to do it. You can do it yourself. So if you write KCL and KVL, you will see that this is 3RCS plus R squared C squared S squared. Right? Now, if that assumption were correct, that individual time constants are equal to individual poles, then that would mean that this sum which can in general be written as in this form, This is generally true. But if you make that assumption, what that would mean is that 1 over P1, P2 should be equal to B2. Well, that's true, I'm sorry. But then if that assumption was correct, then that would mean that this would be tau 1, 0, tau 2, 0. This is the part that's true. And let's see if it's true or not. If the individual poles were just 1 over time constant, so if the P1 was 1 over R, minus 1 over RC, and P2 was minus 1 over 2 RC, then B2 should be the product of the two, which becomes 1 over, which basically becomes 2R squared C squared. But you have R squared C squared here. So this factor of 2 shows you that this is not valid. This is just a counterexample. The good thing about proving something is not correct is that you need one counterexample. One second. So in general, this is not true, even for something as simple as that. So what is true? Now, I said unless. I had an unless in my discussion. What was my unless? I said that individual separation of a time constant may be true under certain circumstances. Now, what is that circumstance? What are the circumstances? So I said that if time constant is uncoupled from the rest of the circuit, then it can be factored out. In other words, if you have an uncoupled time constant, something like this, let's say for the sake of argument, could be, let's say one of the time constants is uncoupled, could be written in the following form. Namely, it can be factored. But for you to be able to do this, this time constant needs to be uncoupled from the rest of the circuit. How do you verify that something is uncoupled? And we'll have a derivation later on. We'll show you how it works mathematically. But the way is simple. You look at the resistance seen by that element associated with that time constant, let's say that capacitor, and see if shorting and opening of everything, all the other capacitors and inductors, if shorting and opening of them has any effect on it. If you can find an element where shorting and opening of all the other remaining elements doesn't change the resistance it sees, then that time constant is uncoupled. So it comes out of so you can actually separate. That's a pole, that's a separate pole. You can actually have groups of time constants that are uncoupled from each other. So you can have a bunch of time constants. So let's say these are time constants, tau 1, tau 2, tau 3, tau 4, 5, 6, whatever. So you can have these two that are coupled to each other, but uncoupled from the rest of us. And you can have these three that are coupled to each other, but uncoupled from the rest, and these guys that's uncoupled from all of them. So if you have something like this, then what that means is that your transfer function can be written as something like this. This is associated with tau 1, tau 2, and tau 4 in this example, times 1 plus tau 3s times 1 plus, let's call this b prime, and b1 double prime s plus b2 double prime s squared. This is associated with tau 3 obviously, and these are associated with tau 5 and 6. You can have groups that are uncoupled. You basically partition them into separate blocks that are uncoupled. But in general, you have to prove it, and that's a condition that doesn't generally happen. It doesn't happen more often than it does. So let me give you an example where this is actually the case. It's one of the stages we are familiar with. Let's look at the common gate. So the common gate, well, how does a common gate look like? So you have, let's say R2, let's say you have R1, En, and let's say you have two capacitors. Called the C pi and the C mu. And this is virtual, this is AC ground essentially, right? So fixed bias, so from an AC perspective, this is ground. So what are the time constants? Let's look model. And this is V out. And the capacitors are here and there. Let's find the time. What is tau pi 0? It's okay, guys. So what is tau pi 0? Well, help me out. What is the definition of tau pi 0? How do you determine tau pi 0? You look at the resistance seen by this capacitor when all the other elements, that's what this 0 means, 0 value time constant. The resistance seen by this capacitor when all the other elements are 0 value. In this case, you have another capacitor, so that's 0 value, so it's not there. So what is the resistance you see across here between the base, the source and ground? In other words, what is the resistance between this node and ground? What do you see looking up? Rm. This is Rm. What do you see looking down? When the sources are null, R1. So it's R1 parallel Rm. Right? So it becomes Rm parallel R1 times C pi. Sometimes I put the C pi up. Tau mu 0. What is tau mu 0? What is the resistance seen by this capacitor when the other one is null? 0. So this one is 0 value, whatever. So what do you see? It's the resistance seen between this node and ground. R2. If you ignore RO, it's basically R2. If you don't, just take this that into account. So it's basically in this case C mu R2. So these are the two time constants. So in general, I know this is what is generally true is that V1 is simply tau pi 0 plus tau mu 0. This is generally true. This is always true. But now, let's see if they're coupled. So would the resistance seen by this guy change if I short or open this guy? No. So that's enough at this point because there are only two of them. So if one is uncoupled, one can be factored out. What's left is also a first order thing. So that can be obviously it's factored into the first order thing. But you can do it the other way around. What is the resistance seen by this? Would the resistance seen by this guy change if I short this or open it? Shorting or opening of this doesn't change the resistance seen by this guy or that guy. Right? So these two are uncoupled. So in this case, in fact, the transfer function is simply h naught divided by 1 plus tau pi 0s times 1 plus tau mu 0s. And obviously, if you have something like this, of course, B1, which would be the product this times that plus this times that, would be the same. But now you also know the B2. Once if you have it in factor form, you know everything. The V2 is basically the product, obviously. But that's only true for the zero value time constants only if they're uncoupled. So this is an example of uncoupled pair of poles. But you see an example of case where they were. And most of the time they are not uncoupled. There are some cases where you can actually isolate some elements and make your life easier. But that also tells you something, we can learn something right away about the common gate. Right? You have two poles. And there are two time constants. So what do we think? Do you think it's a fast stage or a slow stage? Do you remember the common source, for instance, or common emitter? When we looked at it, we saw that we had one big time constant. Do you remember tau mu was large, right? Because tau mu why was tau mu large? Because there was a lot of gain, inverting gain across that capacitor. And that was what the Miller effect was, Miller multiplication. So you had the capacitor saw a much larger voltage swing across it. So the time constant became huge at time. How about here? Do we have a large time constant? Well, how about this one? What is this on the order of? Well, let's say Rm in parallel with R1. So I know Rm parallel with anything is smaller than Rm. So let's say worst case scenario is Rm. If it's Rm C pi, what am I looking at? Rm C pi is basically C pi over Gm, which is smaller than the time constant of the cutoff frequency, omega t. Because you remember omega t is Gm over C pi plus C mu. if you have if you're reasonable and if you have a small R2, C mu is generally smaller than C pi. So this is a small capacitor times the resistance. So as long as you are reasonable as how to choose this resistor, then you're okay. But your response pretty much is dominated here of this stage, not on this side. It's determined by this capacitance. And this is an example, for example, and we'll see many examples where a capacitance that's smaller has a larger effect than a capacitance that's larger. And the better example was actually the common source, or the common emitter. Where C mu, which was a much smaller capacitor, became much larger because of the multiplication if you have a large gain. So that's one example of uncoupled poles. Any questions so far? Yes.
It's a minor thing, but I just want to make sure I understand this right. The general equation for the transfer function that you wrote down on the top four, right behind you, the second order term, the S squared terms, they should have beta 1i, alpha 1i, or at least some, right? Because we're accumulating units now.
Oh yes, actually, I'm sorry. Yes, that's a very good point. Not that it mattered in this discussion, but I dropped the term. There should be a coefficient. So this would be alpha 2ij, and this would be beta 2ij. Yes, sorry, I miswriting those. We need a coefficient in general. That's right. I mean, they have all coefficients. Okay? So, any other questions on this? No? Alright, so what we'll do next is basically trying to see what we can do with this. This is actually quite useful and allows us to make an approximation. So this is an exact calculation, but gives us a way to estimate the bandwidth very effectively. So we are going to talk about that. So far everything we did was exact. But then, let's go and do an approximation. We call this a zero value time constant approximation for bandwidth calculation. So, for ZVT bandwidth calculation. So, here's what we're going to, yes?
Oh, I'm just wondering, is the next set or not?
Yes.
Oh, about
Okay, so let's talk about this zero value bandwidth calculation. And here what we want to do is that let's just make a couple of assumptions initially. So let's start with some simplifying assumptions. So let's say we don't have, so these are assumptions. Let's say we don't have a dominance 0. So this is the basic ZVT, and then we'll see how we modify ZVT and how we can get more accurate results beyond standard ZVT. So standard ZVT is the following. It says, let's say no significant zeros. Okay? So what that means is that basically if either you don't have a zero or if you have them, they are so high frequency that they don't affect the response. And then the other one, the second assumption is that no significant complex poles. By the way, another side note here, just which I could mention, is that another way to see that the time constants are not necessarily, so this individual sum cannot be equal, is that the poles can be complex in general, right? But the time constants are always real. So that's an obvious way that they can't be generally a one-to-one correspondence. But anyway, so let's assume that there are no significant complex poles. Now, with these two assumptions, we want to come up with a way of approximating a low-pass system. So let's say you're assuming a low-pass system. So we have a system that essentially, whose transfer function, you're saying, looks like this. All the way to the higher orders. If you have a system like that, and let's say you don't have dominant poles, and I'll see why that matters in a second. The question is, I know V1. The question is that can I use this information to then estimate my value? How can I do it? Well, what does the transfer function of a system like this look like? Well, it's going to be monotonically decreasing, right? Because you have poles. 20 log of that, obviously, but this is log of omega. I'm interested at my 3 dB bandwidth. Basically, the frequency at which the magnitude of h of j omega, let's call this omega h, is equal to 1 over square root of 2 of A naught. And this is the frequency at which the power is 1/2, if this were a voltage or like a current transfer function, right? Because the voltage squared or current squared gives you the power. So if your transfer voltage gain drops to 1 factor of 1 over square root of 2, this is the frequency at which your gain really has dropped by, your power gain has really dropped by minus 3 dB. So a lot of times we call this omega minus 3 dB, or omega h in the transfer function. So my question is, how can I determine this? Well, let's start from very low frequencies. Let's start from here. When I'm at very, very low frequencies, which one of these terms in the denominator matter? None of them, right? Except for the 1. So none of these are significant. As I increase my frequency, which one is the one that kicks in first? Becomes more important first. This one, right? And then as I increase the frequency further, these other terms become more and more important. But this is the beginning of the drop that I'm interested in. I'm interested in frequency at which it drops only by its factor of 1 over square root of 2. So what if I approximate this at around that frequency, so let me say around omega L, approximated as A naught over 1 plus B1S as a first order system. What is the cutoff frequency of that system? Well, that's an obvious one, right? What is the omega 3 dB of this system? It's simply 1 over B1, right? So I am approximating my omega L, my 3 dB frequency, with 1 over B1, which is exactly equal to the sum of the time, zero value time constants. So this part is exact. This approximation is approximate, right? This part is the approximation. This is the exact. So there is another interesting thing about this which is useful, this approximation, because this allows you to basically estimate the bandwidth by just calculating a bunch of zero value time constants. And more importantly, the most important part of this is that it tells you which one of these time constants is the big culprit. It tells you where your major problem is, and that's why it's important from a design perspective. Because you design a circuit, you look at it, well, okay, let's see. I'm trying to get this much bandwidth, I'm getting 1/100th of that. What is limiting me? And then you go and look at the time constant and see which is the big time constant, or where your limitations are coming from. That's the usefulness, and I will show you examples, real numerical examples of this in a second. But that's how it's used. This is an approximation. Now, the interesting thing about this approximation is that it's a conservative approximation. In other words, it always underestimates your bandwidth. The bandwidth it gives you, almost always, you can make some pathological cases that it's not true, but most practical cases this is not the case, is always lower than what you actually get. So you know if you design something with this, you're in a good shape. And if this estimate that you have the right bandwidth, you probably have more bandwidth than this estimates. In this case, which is a good thing. Sometimes, and even if these assumptions are violated, you will see that it becomes even the problem with these assumptions is that if they are violated generally, most of the time, if they're violated, it makes this approximation so ridiculously conservative that it's useless. So it's always, I can always give you an exact result as a good result. I mean, a correct result in terms of what your bandwidth is. Your bandwidth is at least 0. That's a correct statement, but useless, right? If I tell you your bandwidth is in excess of 0, that's a very conservative position, but it's completely useless. So I have to give you something that's close. I mean, I can't just pick something that's ridiculously low. So the problem is that when these assumptions are violated, and you will see examples of this, then it becomes ridiculously conservative, and therefore we have to make modifications, and we'll see what kind of modifications and improvements we can make. Anyhow, so this is the approximation, and let's try to see what kind of bandwidth estimates we can get based on this. There are different ways we can do this, but We don't need the derivation anymore, do we? We'll come back to these sums. Next step is this, of course, at some point. But probably not today. Do we want to take a little quick break? Just let's cut.